So, Joe, Rosen, and I really appreciate the invitation to speak to you today about the spirit of innovation at Dartmouth in collaborations between engineering and medicine. As was mentioned, Joe and I have enjoyed working together since we met at Cornell in the early 70s. And at Dartmouth, we've been teaching courses together and working on projects for several years. I'd like to start off with some stories exploring engineering and medicine collaborations at Dartmouth, and then hand it off to Joe to talk about his work at Walter Reed and innovations in the area of the wounded warfighter. As was mentioned, 3 years ago, the Thayer School of Engineering decided to develop engineering and medicine as an area of strategic growth for the department. This has led to adding several members of the faculty, as well as new courses in the curriculum. And currently, over 50% of the engineering faculty are engaged in research and or teaching in the area of engineering and medicine, so it's clearly our strength. Joe and I teach two courses on technology and healthcare. The fall course, Engineering Science 13, explores the promise of network computing and information to transform the practice of medicine. For the spring course that'll start in a few weeks, the theme is Redesigning Humans and explores advances in genetics, minimally invasive surgery, robotics, nanotechnology, and other topics. The class covers some wild topics. For example, as a future model for human limb generation, we cover the regenerative process of the marbled salamander. So this little guy can lose a limb, his tail, an eye, and it will grow a new one in just a few weeks. And it turns out that as human embryos, we all had this ability at one point, but we lose it at some point in our development. The question is, how can we turn it back on? We invite several national experts to give guest lectures in this course. One of the early speakers is a well-known science writer, David Ewing Duncan, the father of one of our students, who's the founder and director of the Center for Life Science Policy at UC Berkeley. And he'll be talking about how high-tech testing for genomics, environmental impacts, and neurology for individuals. He actually has been the test subject for this work, and he is the experimental man in the book. He's had more kind of genetic testing on his DNA than anyone on the planet. So that'll be fun. We're having Takeo Kannadi, who runs like the premier lab in the country on robotics at Carnegie Mellon. They have a lot of projects in the medical field. They also have this long-standing, amazing program on autonomous vehicles. So they, for example, have a car that has driven from Washington, D.C. to L.A. with no one ever touching the wheel. Okay? They had to have a student kind of sit in the driver's seat because otherwise they get pulled over. So we have people coming national leaders talk about simulation, including the president of Texas A&M. We also have several guest lectures by faculty at Dartmouth Hitchcock, and it's really a wonderful example of the spirit of generosity of our collegial culture. That these folks are incredibly busy, take the time to put together a lecture that's targeted for Dartmouth undergraduates, and they're really exciting and sort of wonderful to do it. We have a panel this year on the brain that'll include MIT's Marvin Minsky, and other folks from Dartmouth. That'll be really interesting. One of the topics we cover are brain-machine interfaces, which is this amazing new bit of research. So here's a project from Pittsburgh showing a monkey who's been trained to control a robotic arm just by thinking. That is, he's feeding himself. He's not pushing a joystick, he's just thinking about moving the arm, and it moves. There's obviously a lot of training that goes involved in this, but it has incredible implications for humans as well. The finale of this course is a lecture titled Destiny by Design, The Technology of Immortality by Louis Duncan, who is the president of Rollins College in Florida. He was formerly the dean of the Thayer School of Engineering. And Louis Duncan shocks the class in understanding how convergence of technology will allow them to become the first generation to live forever. and they never get over it, really. We teach this course in a large auditorium, so check out the syllabus on the web, and come up to sit in on any lectures that you'd like to see. It's a standing invitation. In 1991, when Joe first moved from Stanford to Dartmouth, he led a startup effort to explore advanced computing, modeling, and simulation for difficult surgical tasks. So the founding team included 3 software geniuses from the Media Lab at MIT, Steve Piper, Mike McKenna, and Dave Chen, if you know them. They're in town here. Dean Charles Hutchinson, and myself. And after a few years of development, we settled on a target application, abdominal aortic aneurysm repair. In the early 90s, aortic aneurysm repair was moving from traditional open surgical repair, shown here, a nasty, difficult operation with a lot of morbidity, to endovascular stent graft repair. And in the 90s, all of the manufacturers noted here had major projects in the order of $100 million each, developing minimally invasive stent graft devices that could be delivered via catheter as an interventional radiology procedure. So instead of a big nasty operation, now it's like a one-day procedure, a femoral artery stick, and you can go home. These devices looked and sounded wonderfully simple. However, the reality was one of complexity and hidden challenges. This is, a few years ago, if you wanted to order a Gore Excluder device, you had to make all of these measurements, fill out all of these charts and make all these measurements. In the field of interventional, and that's just ordering the parts, In the field of interventional radiology, endovascular AAA repair is known as a 9 out of 10 degree of difficulty. So at MMS, the solution we developed was a computer-aided design software system for solving the challenging tasks for this procedure. I won't go into these in detail, but just kind of flip through them. This is what the interface looks like. We solved ways to measure vessel diameters accurately, to measure graft lengths accurately, even through a tortuous vessel, even measure kind of wonky things like making a C-arm gantry correction angle so that you got things in the right place. You could do a virtual analysis to make sure that this device you're going to put through the femoral artery would actually fit in that vessel. You were actually able to do a treatment simulation and try out the device that you had planned for as a virtual stent graft. And then finally, there's a system for long-term surveillance for following these patients over time. So enormously complicated. The key part of this progress for us was the enlistment of a young vascular surgeon at Dartmouth Hitchcock, Mark Fillinger, who became our key clinical collaborator for this project. And this was when Mark and his wife Mary had just been married a few years before they had children. And literally for 3 years, he would spend 15 hours a week in our lab. And he would leave the clinic at 5:30. He'd show up, we'd get involved in things. It'd be 7:30, 8 o'clock, he'd call Mary, sorry, we can't come home tonight. So we'd order pizza, he stayed till 9, 10. I mean, this went on for 3 years. It was enormously complicated. We needed a clinician who really understood this to help us through it. So the punchline of the story is the project was ultimately very successful, and preview software has become widely used now as a standard of care for endovascular AAA repair. Another story. One of the most durable and fruitful research efforts at Thayer is the 35-year collaboration of Professor John Collier and Dr. Michael Mayer from the Hitchcock Clinic, who are co-directors of Dartmouth's Biomedical Engineering Center. Their work is focused on the analysis and design of orthopedic implants. Mayer served as Collier's doctoral thesis on his thesis committee in 1975, and they've been working together ever since. So a key aspect of their work is the clinical material science analysis of retrieved implants that have been used in the body and removed during revision or autopsy. Their library of retrieved devices currently numbers greater than 10,000 implants, the largest in the world. Through their collaboration, Collier and Mayer have been incredibly prolific, producing a steady stream of journal articles and workshops for clinicians in industry. A few indicators of their stature in the field: Mayer is a former chairman of the FDA panel on orthopedic devices, and Collier was named to the American College of Orthopedic Surgeons. Gunnar Anderson, who's a spine specialist from Rush U, calls the Dartmouth lab and implant library a national treasure. So that tells you something about how they're thought of in the field. It seems like every year Collier and Mayer have some new discovery that rocks the field of orthopedics. One of my favorites is how they solved the mystery of early failures from polyethylene knee implants. New polyethylene implants look like this: shiny and smooth, designed to make a durable, low-friction bearing when coupled with a cobalt chrome femoral component, nice and slippery. The trouble is that some of the implants were failing after only a few years, and when removed, they look like this, completely disintegrated. For 5 years, Collier and Mayer tested everything to find the cause: differences of user impact, their weight, their diet, differences of manufacturer, difference of implant design, until they finally discovered the cause. Polyethylene knee components were routinely sterilized using gamma radiation to kill any bacteria before shipment from the manufacturers. Collier and Mayer discovered that gamma sterilization caused severe oxidation of polyethylene and resulted in the rapid degradation of its material properties. Okay, so here's the paper that Collier presented at the AAOS, American College of Orthopedic Surgeons, in 1996 that reported this finding to the orthopedic community and clinical practice. As you can imagine, for the manufacturers with hundreds of millions of dollars of gamma sterilized inventory, this is not welcome news. He has an amazing story about how that went. That's a great story. Tilman Gerngross. Tilman Gerngross is the rock star of biomedical innovation at Thayer. He's shown here with Dean Charles Hutchinson, co-founders of Glycofy. Protein-based therapies represent more than half of the drugs currently in development, and they have to be manufactured by living cells, conventionally using mammalian cells. At Glycofy, Professor Gerngross re-engineered yeast, like the type used to make beer, really, to secrete human complex glycoproteins. This project revolutionized the way therapeutic proteins are made. Glycofy was founded in the spring of 2000 and was acquired by Merck in 2006 for over $400 million. Okay. So, you would think, after his success, Tilman Gerngross would kind of retire to the Cayman Islands, kick back, do something. But no. Almost immediately he launches this new project, Atomeb, with an MIT professor here in Boston, the goal to create a fully integrated yeast-based antibody discovery platform, and he's still teaching a full course load. So, what a guy. I'd like to include an undergraduate project here. A lot of students get involved in medical devices and projects. And this particular one addresses the problem of infusion-related bacterial infections, estimated in the literature at 50,000 to 120,000 per year, with an associated mortality of 15%. Dr. Corey Birchman, an anesthesiologist at Dartmouth Hitchcock, was a clinical collaborator with the students for the project. At the beginning of this project, the Dartmouth Hitchcock folks with the students completed a study that included taking cultures from various points of anesthesia machines and the interior lumens of the stopcock ports before and after surgery. Bacteria levels from before and after were compared, and the results were that 32% of the stopcocks were found to be contaminated, and 75% of those led to contamination of the fluid line. And this is probably typical across clinical practice. So if you look at the standard modality for cleaning these devices, it's called here, scrub the hub, this little thing. And the Dartmouth study highlights the limitation of such techniques for cleaning these lumens. The student solution uses an ultraviolet light source to sterilize the intravenous fluid with the device placed last in the IV system to capture any contamination. Their prototyping has gone through several iterations. The latest one kills everything but anthrax. Steve Reinitz, the key student on the project, and Dr. Birchman have submitted for a patent, and Steve says they've arranged an analysis by a group of first-year Tuck students who will spend the spring term looking at possible routes to market and so forth. So I love these stories of students that sort of jump into these things that are likely to have a huge impact eventually on clinical practice. One of the most famous stories of collaborations in engineering medicine is the collaboration between David Roberts, a neurosurgeon, and Thayer professor John Strobane, who faced the central challenge of trying to do stereotactic surgery without stereotactic frames. So what they developed essentially was a better solution, an instrument that could map CT data onto the visual field of a microscope to produce three-dimensional view of the brain. And basically, they worked together in Strobane's lab at 7 in the morning. This is 1980 to 1983. Before Robert's clinical hours and Strobane's classes, and they created a microscope, operating microscope that was stereotactic, frameless, and precise. They tested the prototype in an operating room in 1983, patented the invention 3 years later. Frameless stereotactic operating microscope was a huge hit. Not only was more comfortable for the patient, it was the beginning of image-guided surgery. So here's the sort of standard operating microscope view of brain tissue, and here's the scope view with stereotactically registered data overlaid on the surgical field showing the tumor border segmented from CT scan data. Today, every neurosurgical operating room in the world is equipped with an updated version of Strobane and Roberts' invention, like this DMEDGE system shown here. Now, brain surgery would be unthinkable without it. 25 years later, David Roberts continues collaborations with several engineering faculty on multiple projects in stereotactic and functional neurosurgery, including computational modeling of brain deformation and fluorescence-guided neurosurgery. I recently had a chance to ask Dave Roberts about his biomedical research with Thayer and why it seems to have been so fruitful. And here was his answer. He said, Dartmouth is a great place for R&D. We can think about, develop, and pilot all sorts of new ideas. We do this better than probably everybody else. Even with the incredible resources and work of some of the institutions in Boston, Dartmouth competes extremely well. I thought I'd throw that one in. Boston. So he also said, I think this is in part a matter of scale. Departments and schools are not so big as to become wholly autonomous and insular. It's just so easy to work with multiple disciplines here. At Dartmouth, people often get defensive on the topic of size, but in this matter, it is clearly a strength. I love that. Secondly, there's truly an academic community here at Dartmouth. One in which there's an interest in ideas and their discussion across large portions of the student and faculty bodies. A culture that encourages dialogue and collaboration. We're a bit idealistic about it in this regard, but that can be a really good thing. The shots that are up here are from a wonderful event. It was organized by Augusta Niles, who's here this evening somewhere. This you organized a few years ago called IDEO University. And for this exercise, a group of 70 students from Tuck, Thayer, and undergraduates and grad students spent a whole day learning creative design process from visiting professionals from the firm IDEO. So it was a wonderful event that she orchestrated. And certainly the collegial atmosphere at Dartmouth, which is starkly absent at many prestigious competitors, is enormously important in our success. I must say, at Thayer we enjoy an especially close-knit community of students and faculty that in many ways often feels like a big family. And finally, there's the advantage of a long, successful tradition of innovation, as with Keith Paulson's group here in medical imaging. In the end, of course, the success of this research comes down to the strength and creativity of the individuals and their relationships. So, thank you.